Hey everyone, this is Ghada Al-Mashagba. Thank you for joining my talk today, in which I will introduce our new multi-party computation model, Gage MPC. The goal of this model is to prevent the leakage of the residual function that is inherent in an interactive MPC. This is a joint work with Fabrice Ben Hamouda, Sungwo Khan, Daniel Yaroslavix, Tal Malkin, Alex Nikita, Karl Rabin, Abhishek Shah, and Iran Tromer. Gage MPC is about combining two paradigms, namely non-interactive multi-party computation and MPC over a blockchain. I will introduce both of these paradigms, starting with NIMPC and using auctions as an example. In a conventional NIMPC setup, we have a special entity called an evaluator that will be available for the entire period of the computation. And we have a set of participants who want to compute a specific function over their private inputs. Each party will submit a message to the evaluator where this message is computed based on its private input. And without interacting with any other party, once all these messages are received, the evaluator performs the computation and announces the output, which in our case will be the winner in the auction. Existing works on NIMPC showed that in order to enable this setting, a trusted setup is needed. This trusted setup will generate what we call correlated randomness that will be distributed among the parties beforehand. Each of these parties will then generate its message based on her private input and this correlated randomness. In the NIMPC setting, we have that the leakage of the residual function is inherent. Meaning that if the evaluator colludes with any of the parties, say party 0, then the evaluator can recompute the function over arbitrary values of this colluding party input while fixing the inputs of the rest or the honest parties. So translate that to our example, even for example, let's say the last party in the computation, PN, can wait until it sees all messages from the rest of the parties, and then by just like doing or recomputing the leakage function, it will be able to figure out the highest previous bid and then act accordingly. These existing works showed how to construct NIMPC protocols that are robust to collusion. So to guarantee that the only thing that will be leaked is the residual function. And as I just said, all these protocols require a trusted setup to generate correlated randomness for the players. In parallel, there's progress on exploiting blockchains in MPC. This started with the first generation who used a blockchain to implement a broadcast channel that is usually needed in MPC protocols. The second generation incorporated payments into MPC protocols, and this was mainly used to address fairness, where the party that quits the computation before letting others know the output will lose her collateral or penalty deposit. The third generation, which is this work, we take this further to incorporate smart contracts and miners as active participants in the MPC protocol. So our goal is to utilize the blockchain in a novel way to prevent the leakage of the residual function in NIMPC and avoid the requirement of having a trusted setup or the evaluator party who has to be available online during the whole computation. This is done as follows. At a high level, a Gage MPC is composed of a party P0 and a set of N parties who all want to compute a specific function over their private inputs. P0 sets up the computation by preparing its initial message M0. Then she creates a smart contract to control the computation and uses this smart contract to record M0 and to create a collateral on the blockchain. The amount of this collateral is proportional to the hardness or amount of work that others need or needed by others to finalize the computation. After posting M0 and the collateral, other parties will use M0 to compute, and of course their private inputs, to compute their own messages, and then they post them on the blockchain using the same smart contract. After having all these messages published on the blockchain and within a timeout period, an honest P0 will come back and post a final message, M0 prime, that will allow finalizing the computation and announcing the output. This honest P0 will be able to recover her collateral because she submitted M0 prime. On the other hand, a malicious P0 may not show up, and at that time, when just like after a timeout, other parties in the system, which we call bounty hunters, will expend the needed computation or work needed to compute M0 prime that will be used to finalize the computation. As a reward, these bounty hunters will claim the collateral that was deposited by P0. So as long as there are financially motivated bounty hunters who are willing to do the work to finalize the computation, the output of the MPC protocol is guaranteed. So it is either, which we call the nominal path, P0 will allow producing the output, or the motivated bounty hunters will do so. This setup works under a monetary assumption where we assume that an honest party, P0, can put a collateral of value much higher than what an adversary can expend on computation. Gage MPC eliminates the leakage of the residual function by requiring the adversary to expend an equivalent computation cost to what honest bounty hunters will expend in order to evaluate the functionality F over a single input. So this means that evaluating this functionality over kind of like different set of inputs will be expensive. Also, Gage MPC doesn't require a trusted setup, and it doesn't require a dedicated online evaluator, because finalizing the computation is automatic, done by the miners when executing the smart contract that controls the Gage MPC protocol. However, leaking or kind of like the protection against the leakage of the residual function is guaranteed only in the short term. This is because kind of like having a wealthy patient adversary who's willing to invest a large amount of computation, this adversary will be able to leak the residual function and maybe kind of like leak information about the private inputs of the parties. For this reason, Gage MPC should be used with computations of an ephemeral nature, like auctions, for example. In the rest of this talk, I will present our Gage MPC construction at a high level. The full technical details can be found in our paper. As you see in the figure, we introduce several primitives and combine them together towards building our Gage MPC scheme. We start with a time capsule, which is basically committing to a value that can be opened after expending a pre-specified amount of computation. For example, I can commit to a value S by publishing its hash on the blockchain, for example, and to open it, anyone will brute force the pre-image domain of this hash function until she finds the value S or the pre-image S. And as you can imagine, the longer the seed value is, the harder or the larger is the amount of computation that is needed in the opening process. Basically, this is what bounty hunters are doing in Gage MPC. So the input labels will be committed in time capsules. If B0 doesn't come back to open them, the bounty hunters will brute force the opening and allow finalizing the computation. Having the bounty hunter post the opening publicly will not work in our setup. This is because other malicious bounty hunters may claim this opening as theirs and steal the collateral from the honest bounty hunter who did the work. For this reason, we combine time capsules with zero knowledge proofs to allow a bounty hunter to prove in zero knowledge that she found the opening and did the required amount of work without revealing the opening itself. The combination of these two primitives we call POTC or proof of time capsules. In order to allow rewarding the bounty hunters for the work they are doing in opening time capsules, we utilize a smart contract to build what we call Gage time capsules, where we bundle several POTCs together and allow P0 to create a collateral on the blockchain through this smart contract that controls the Gage time capsule. And not all these POTCs will be opened later, only those that correspond to the private inputs of the parties. So as you see in the figure, and as we mentioned before, there will be two paths. The nominal path where P0 will come back and open the intended POTCs and recover her collateral. And there is the bounty hunting path where bounty hunters will do the work to open these time capsules and claim the collateral. Gage time capsules basically allow committing to the input labels that are needed for the computation. However, we still need a protocol to perform the computation itself over these inputs. For this reason, we introduce what we call label-driven MPC, which is a generalization of garbled circuit that is robust to the exposure of additional labels. Recall that in Yau's garbled circuits, we have two parties, the garbler P0 and the evaluator P1. P0 garbles the circuit that represents the functionality that these parties want to compute over their private inputs. And this garbling is basically encrypting the truth table of the circuit. It will also generate random labels for the input wires, where for each wire we will have two labels, one for the bit 0 and the other for the bit 1. P0 sends the garbled circuit to the evaluator P1, and then they engage in an oblivious transfer protocol to allow P1 to retrieve the one label that represents or that corresponds to her input. After that, P1 can evaluate the garbled circuit using these labels and obtain the output of the function f over their private inputs. The security guarantee of Yau states that nothing will be revealed or leaked about the private inputs beyond what can be deduced from the output. And it is known that revealing even of one additional label will compromise security. So, for example, if an adversary gets to see both labels of an input wire, this may allow him to leak information about the private inputs. We handle that by making YAW robust to or against revealing K additional labels. This is done by adding another layer of indirection to the computation, which is the circuit C prime that you see in the figure. Circuit C prime will output the actual labels needed for the computation or the garbled circuit C if and only if its inputs constitute a valid code word. By using a linear error correcting code with a minimum distance of K plus 1, evaluating the circuit C over a new input value will require K plus 1 additional labels. Thus, we achieve K robustness in this case. As you might have guessed by now, Gage MPC simply takes a label-driven MPC and commits the input labels in a GATC. Party P0, who sets up the computation, will prepare the garbled circuit and GATCs for input labels for the rest of the parties and create a smart contract to control the computation, which will also create a collateral for this party. The rest of the parties will submit their inputs, and then honest P0 will come back and open the corresponding labels, which are POTCs, or the bounty hunters will do that. After getting the openings, the smart or the controller smart contract evaluate the circuit over these labels and record the output. Robustness guarantees that for an adversary to evaluate the garbled circuit over another input, she will need to expend computation equivalent to the work needed to open an additional K plus 1 POTCs or time capsules to get a valid code word. In the paper, we provide several transformations for Gage MPC that provide several security levels. As you can imagine, conventional YAW garbled circuits where only P0's input is private provides what we call public input and zero robust security because it is insecure against the exposure of any additional label. By using error correcting codes, we obtain robust label-driven MPC. And to handle private inputs, we can use two-round, two-party computation protocol to allow that. By combining these two constructions together, we obtain a Gage MPC that satisfies the highest security level, which is supporting private inputs for all parties and robust against the exposure of additional input labels. And as mentioned, the fully private input versions are for the two-party setting only. To conclude, in this talk, we introduced a new model called Gage MPC, which incorporates smart contracts, the miners, and financial incentives in the computation. Gage MPC does not leak the residual function and doesn't require a trusted setup like previous non-interactive MPC protocols. And it represents the third generation of combining MPC with blockchains. Also, on the way, we developed several new primitives like proof of time capsules, Gage time capsules, label-driven MPC, which we believe that they are of an independent interest and could be useful in building applications other than Gage MPC. Also, in the paper, we show a proof of concept implementation of a simple auction functionality to show or to assess the efficiency of our protocols and primitives. Thank you for your attention, and happy to answer any questions you might have. Thank you.